All right, so let's take a look at this problem here. Determine the values a, b, and c such that the function f satisfies hypotheses of the mean value theorem on the interval from 0 to 3. Okay, so first of all here, what are the hypotheses for the mean value theorem? That's rolls.
No, f of b minus f of a over b minus a equals f prime of c.
Okay, that's what it says, but what were the hypotheses? What were those conditions that had to be met?
That's differentiable and continuous.
Okay, so it has to be continuous on the closed interval from 0 to 3, and it has to be differentiable on the open interval from 0 to 3. So there's a couple of things that we need to look at here. We've dealt with how to make piecewise functions continuous before, right? What's the key with those?
They have to line up at the same point. Like when you look at the very last point on the definitions, and then
Okay.
and you plug those in.
All right, like these junction points where x is 0, or in this case where x is 1, we need to make sure they connect, right? So if I'm doing continuous, first of all, I need to make sure that when x equals 0, 1 equals a times 0 plus b. So that's kind of nice. B has to equal 1. Okay? And then I also need to double check the junction over here at 1. Alright, so when x equals 1, a times 1 plus b has to equal 1 squared plus 4 times 1 plus c.
Isn't the b going to be 1?
Okay, well yeah, now we already know b is 1, so I know a plus 1 has to equal 1 plus 4, so 5 plus c. Okay, so I'm still a little bit stuck here because I don't know what a or c are. Okay, that's the other part here. So this will make it continuous, but to make it differentiable, I'll do this part in red. Okay? To make it differentiable, it has to be smooth. I can't have any sharp changes in direction. So, I need the slope at the junction here at 0 to be equal on both parts. Okay? So I need, when x equals 0, I need the derivative of 1 to equal the derivative of ax plus b. And we'll go ahead and put in the 1. Alright? So, what's the derivative of 1? 0.
And the other side.
The derivative of the other side is a. If I plug in 0 for x, there are no x's left, so I know a has to equal 0. So that right there should tell us that 1 equals 5 plus c. That means c has to equal a negative 4. Okay? Now, I still do need to double check this other junction here at 1. Okay, so let's check this here. We have, when x equals 1, the derivative of ax plus 1, which is really just what? a, which we already know is supposed to be 0, right? Should equal the derivative of the x squared plus 4x plus c, okay? Which is 2x plus 4, okay? Now, if a is 0, and this is where x is supposed to equal 1, right? Did that work out?
No, a equals 6.
Okay. Here, that's telling us a would have to be 6.
But wouldn't you have found that originally if you did x, the derivative of x times ax plus b equals derivative of x squared plus 4x plus c first rather than doing 1 and x plus 1? Like,
Okay, I would have found a to be 6. So now let's go back and let's think about this situation here. Okay? It has to be differentiable on the open interval, right?
yeah.
So, what value of a should I have?
6.
Why?
Because if you're using like when x equals 0, and that's like on the closed interval, because that's when
Yeah, I don't actually need it to be smooth over here at 0, do I?
No.
Okay? So if I let a equal 6 and then I come back over here, okay, and let's get rid of this, and let's redo this with a being 6, that means 6 plus 1 equals 5 plus c, so that means c has to equal 2. 7 minus 5. Alright? So now I know that my function f of x equals 1 when x equals 0. It equals 6x plus b was 1, when x is between 0 and 1, including 1. And then it's x squared plus 4x, c is 2, so plus 2, when x is between 1 and 3 inclusive. Okay? So it actually only needed to be smooth at the junction where x equaled 1. Okay? So, that's a good illustration there of the difference that the closed interval for continuity makes with the open interval for differentiability. Okay? Alright, so the rest of this lesson here, we really just want to formalize and practice something that we talked about before, and that was the first derivative test. Okay? Now that we've talked about these terms relative min and relative max a little bit more, alright, we're going to formalize this. Okay? So, here we have a couple of different diagrams, and I want to draw the sign diagrams that you would see here. Okay? Now, one thing that's a little tough with this picture is that it's hard to see the tangent lines. So here we have a tangent line, here we have a tangent line, and you can see clearly that if I have c on my number line, then the derivative is negative here and positive here, which means my function is decreasing and then increasing. Okay? So I have a relative min. Okay?
Would there not be a tangent line or a derivative of 0 at c?
Yeah,
It would, right?
that's why we labeled
So
C.
you just didn't show the derivative.
Yeah. Yeah, the tangent is horizontal here, so it's 0 there. Okay, so we've already done the derivative equal to 0 and found those values. Okay? Then we have this one over here. Tangent line is going up, so f prime is positive to the left of c. and it's negative to the right of C because our tangent line is going down. Okay, so F is increasing to decreasing, which gives us a relative maximum. And then we had these, points where we did not have a change in concavity, or not concavity, in direction. So we were increasing to increasing, or decreasing to decreasing, and what did we call these points again?
Points of
Those were
inflection.
plateaus. Okay, they do end up being points of inflection, but we haven't gotten there yet. So, these are plateaus. Okay? Now, there is a term here that you ought to be familiar with, and that is the strictly monotonic on an interval. Okay? Strictly monotonic. This means that on an interval, it's either increasing over the entire interval or it's decreasing on the entire interval. Okay? Now, when we have a plateau point, is it increasing at the plateau point? No. So technically speaking, we shouldn't say it's strictly monotonic all the way from A to B.
So wouldn't only a line be straight?
Well, you could have a line, you could have, say, an exponential function, you could have a logarithmic function, and two, notice this is just for an interval, so we could have a parabola, but just be looking at the interval from here to here. Okay? So, it can be over just an interval. Alright, so let's do a little bit of practice here, okay? Now we have a table. If you don't like using this table, that's okay. Alright, I will show doing the number line and then we can adapt it to the table as well, just so you can see both and take your pick. Alright, so if I want the relative extrema, anytime you're asked for the relative extrema, you're going to do what? Derivative equal to 0 or undefined. Okay? So in this case here, we've got, let me get off of the highlighter. There we go. So, there we go. Alright, so f prime of x is 3x squared minus 3x. So this equals 0. If I factor out a 3x and I have an x minus 1, this gives us critical numbers at x equals 0 or 1. Okay? Now, my personal preference is actually to use a sign diagram, but this table is helpful in letting us see a few things here. Okay, so I'm actually going to give myself some room to write. Okay, so let me get rid of this part here. Okay. Okay, so let's get back to normal writing. Alright, so what I would do is I'd set up my sign diagram with 0 and 1 here, f prime. If I plug in a negative into my f prime, 3 times a negative is a negative minus 1 is a negative, so I have a negative times a negative makes my derivative positive. So I know that my function is increasing. Okay?
You plugged you just plugged negative, like a number less than 0?
Yeah, any negative, if I multiply 3 by a negative, it'll be a negative, and if I subtract 1 from a negative, it'll be a negative. Yeah. So now if I plug in something between 0 and 1, that's positive, so like a half. 3 times a half is positive, a half minus 1 is negative, positive times negative is negative. So I know that this is decreasing. And then if I plug in something bigger than 1, I have 3 times a positive, say 2, so that's positive, and then 2 minus 1 is positive as well. So this is back to positive. Okay? So this tells me right here that at 0, I have a relative max. Relative max, okay? And at 1, I have a relative min. Okay? Now, it asks me to find those extrema, so I should plug in those values. So if I plug 0 into the original function, I get 0. So my relative max value is 0 when x equals 0. Okay? Or I could say the max point is the point 0, 0. Okay? And then the relative min, if I plug in a 1, I have 1 minus 3 halves, which is a negative half. So the relative min value is negative 1/2 when x equals 1. So my min point is 1 negative 1/2. Okay? Now, let me illustrate here the table, how you could use this. All right? If I have two critical numbers like this, it divided the whole interval into 3 intervals. All right? Let me do this real fast here. So negative infinity up to 0, between 0 and 1, and from 1 to positive infinity. Just give me a sec. Okay? If I tested negative 1 or a half or 2, the interval ended up being, the derivative was positive, so the interval was increasing, and then decreasing, and then increasing. Okay? You could even put f prime of negative 1 was positive, f prime of a half was negative, and f prime of 2 was back to positive. So the conclusion is that right here between these intervals I have a max, and between these two intervals I have a min. That's where the table kind of breaks down a little bit, but okay, so that's how you could use either one. You could take your pick. Alright? Alright, so what we're going to do here is we are going to find the relative extrema of f of x is 1/2 x minus sine x in the interval from 0 to 2 pi. And you can see their answers there already, but let's go ahead and look at how we would do this. Alright? First of all, we're going to find those critical numbers. Alright, so I'm going to bring this over here, and I have f prime of x is 1/2 minus cosine x. Alright, I'm going to set that equal to 0, and I have cosine equals a half. So what's x between 0 and 2 pi? Because we all know our unit circle.
Yeah, alright. Yeah. It'd be pi over 2. No, it'd be pi over 4.
Wait, they're coterminals.
No, come on.
Oh wait, cosine. What's it called? 1/2. It would be pi over 6.
Pi over
3.
3.
Yeah.
Okay? And then I also need the fourth quadrant, because that's where cosine is positive. So that would be
Negative.
5 pi over 3. Negative pi over 3 does work, but we want all of our angles to be between 0 and 2 pi. So we'll do the
it's
positive.
It's not including 0 and 2 pi, right?
in this case, it does not actually include 0 and 2 pi, so yeah. And actually, if we're only looking for relative, then it really doesn't matter if it's closed or open. So here we have those, and I'm going to set up a sign diagram. I'm actually going to do this problem this way, and then I'll show you how that little table works. If you like that, you can do that. So now I'm doing the sign diagram. If I plug in for my derivative, if I plug in something below pi over 3,
It's gonna be negative.
like pi over 6,
It's gonna be negative.
okay, cosine of pi over 6 is root 3 over 2, which is bigger than a half, so that's going to be negative. So that means my function is decreasing,
I know.
okay? And then between those two, I can pick anything like pi over 4, okay?
Or pi.
Or pi, yeah, pi. Cosine of pi is a negative 1.
So it's
A half minus a negative 1 is positive 1.5. So I'm increasing here. And then if I plug in something bigger than 5 pi over 3, like maybe 11 pi over 6, okay, cosine of 11 pi over 6 is going to be a root 3 over 2 again. A half minus root 3 over 2 is still negative, so I'm decreasing again. Okay? So, we have a max point. We have a max at the point.
Should we test for the intervals first? The endpoints first?
We don't need endpoints here. We're not doing absolute, we're doing relative. Okay? So 5 pi over 3, if I plug in a 5 pi over 3 in the original function, sine of 5 pi over 3 is a negative root 3 over 2. So 1/2 times 5 pi over 3 is going to be 5 pi over 6 plus root 3 over 2. And I don't care if you leave your y coordinate that. You could just leave it that. That's the exact value rather than rounding. Okay? If I were to find the minimum value, the minimum is at pi over 3.
Yeah, but that's relative, right?
It's a relative min. So at pi over 3, and then if I plug in pi over 3, sine of pi over 3 is a root 3 over 2. So again, I have pi over 6 minus root 3 over 2. Okay? So that's how you would use the sign diagram to find those. Alright, so on example 3 here, we want the relative extrema of f of x equals x squared minus 4 to the 2/3. So, as we have with all of these, we find the derivative. F of x, or f prime of x, is 2/3 times x squared minus 4 to the negative 1/3 power times 2x, because we have the chain rule. Alright, so we have that, and now we need to figure out where this equals 0 or is undefined. So I'm actually going to simplify a little bit here first. I have 2x times 2, so I have a 4x in the numerator, and that's over 3 times the cube root of x squared minus 4. Okay? So, I need to think about what would make this equal to 0 and what would make it equal to 0.
0.
Just x equals 0, yeah, okay? But then I also need to think about, hey, what would make this undefined?
X equals plus or minus 2.
Okay, x is plus or minus 2. That would make the denominator equal to 0, okay? Now, I could also look at that radical and say, am I ever going to get imaginary numbers?
Potentially.
And the answer actually in this case is no. Why?
I don't know.
Is the square?
Different.
It's not a square root,
It's a cube root.
it's a cube root, right? And the cube root is defined for all real numbers. See how your parent functions are coming back into play? Alright, so the cube root is defined for all real numbers, so I don't need to worry about imaginary roots here. So I just have these three critical values, okay, which if we looked over here we saw we should have gotten that. Alright, but we don't know that yet. So let's set up a sign diagram, and again I'm going to do this once with the sign diagram, and I'll show you how it works with the table as well. So I've got here a -2, a 0, and a 2. Please make sure you put them in order, smallest to largest. Okay? That'll really mess you up if you don't. And then we plug numbers into f prime, and that tells us something about f. Alright, so if I plug in a -3 into my f prime, I'm going to have a negative in the numerator, and the denominator is going to be positive. Okay? -3 squared is positive 9, minus 4 is positive, cube root of a positive is positive. So this is negative divided by positive, which is negative. So my function I know is decreasing to here. Okay? Then I plug in, say, a -1. Well, numerator is going to be negative, but on the bottom I have the cube root of 1 minus 4. So that's a cube root of a negative, which is negative. Negative divided by negative is positive. Okay? So then I have between 1 and 2, I'll have a positive in my numerator, but again in the denominator I have the cube root of 1 minus 4, which is negative. Positive divided by negative is negative. And then if I plugged in 3 to get this range past 2, I'd have a positive on the top and a cube root of 9 minus 4, which is positive on the bottom. So it's positive, and we've got that. Okay? So I know a couple of things about this function. First of all, I have relative mins at x equals -2 and x equals 2. Alright? What is the relative minimum value though? Okay, well if I plug in 2 or -2 into the original function, I'm going to get 0 to the 2/3. Okay? So the relative min is 0 at x equals plus or minus 2. Alright, so those points, -2, 0, and +2, 0. Okay? I also have a relative max. Okay, if I plug in 0 to the original function, I have -4 to the 2/3 power. Okay? -4 squared is a positive 16. The cube root of 16 is going to be 2 cube roots of 2. Alright, so I have 2 cube root of 2, okay, at x equals 0. Alright, so the point is 0, 2 cube root of 2. If you have a calculator available and you want to give the decimal, that's fine, of course. Alright, but that's what it would be exactly. Okay? Now, if you wanted to use this table here, I gave us one too few boxes here, so let me give us another box. I'll just split this last one. Alright, so the intervals, here's where you're thinking about it slightly differently. The intervals go from a -infinity up to -2, so the 2 is right here, and then the 0 is here, and the +2 is here. Okay? So then you have the interval from -2 to 0, you have the interval from 0 to 2, and you have the interval from 2 to infinity. Now the reason why this is helpful, you know, we tested x equals -3, and we tested x equals -1, and we tested x equals 1, and we tested x equals 3, and the sign of f prime ended up being negative here, negative here, and positive here. Okay? The conclusion is, though, that we had a relative min right here at 2, at -2. We had a relative max at 0. And we had a relative min at 2. Alright? So then we would make these same statements. Okay, so the table is very similar to our sign diagram. But where it's helpful is sometimes you will be asked, state the intervals where the function is increasing. Okay? Well, on what intervals is this function increasing?
-2 to 0, 2 to +2,
Positive infinity.
Yeah, okay, so here we're increasing on, and I would use open intervals, -2 to 0, or also from 2 to infinity.
It wouldn't be brackets because you're including the -2.
Well, at -2, what's our rate of change?
Oh, 0.
But it's actually undefined, right?
Fine, yeah.
So we would not include -2,
Okay.
and at 0 the slope was 0, so it's not technically increasing or decreasing
okay.
there either.
Yeah.
So here we're going to say it's decreasing on the interval from -infinity up to -2, and also from 0 to 2. Okay? So, just one more example of how to do this. Alright, so let's take a look here at example 4 on the notes. We are trying to find the relative extrema of f of x equals x to the 4th plus 1 over x squared. So, of course, relative extrema, automatically our mind says take the derivative, okay? These are connections we've got to make in our heads. So, I'm taking f prime of x, and how am I going to do this?
Quotient?
We can.
You could just bring it out to the top and product over
Yeah.
the x to the 4th plus 1 times x to the -2.
We can use product rule.
Or you could break it up into x to the 4th over x squared plus 1 over x squared.
Yeah, if you look at this, x to the 4th over x squared plus 1 over x squared, that actually makes it super easy to take the derivative. That's a whole lot easier than doing the product or quotient rule or anything like that. 2x minus 2x to the -3rd. Yes. Okay? Now, the trade-off is actually finding where this equals 0 or is undefined. Maybe a tad bit more complicated, but I still think it's worth it. Okay? So let's set this equal to 0. And I've got 2x minus 2 over x cubed. So I'm going to go ahead and get a common denominator by multiplying this by an x cubed over x cubed. So that's going to make it an x to the 4th on the top. Okay?
We can take the 2 out.
We could take the 2 out. We could divide everything by 2, and then it's just going to be a 1x to the 4th minus 1 over an x cubed equals 0.
Which is going to make it equal.
Okay? So, this equals 0 when the numerator is 0. So what are our answers? 1 and -1, also plus or minus I, but that's not graphable, so we don't care. Alright, so this equals 0 when x is plus or minus 1. But we also want to know when our derivative is undefined, and what value is that at?
X equals 0.
Okay, undefined at x equals 0. So we have 3 critical numbers here. Okay, 3 critical numbers. Now, one thing we should note, and this we haven't run into yet, But we should note that in the original function, 0 was not in the domain either. In the original function, so that means that and it's not removable, like we couldn't reduce it and get rid of it. So that means at 0, what do we have?
No.
An asymptote, okay? An asymptote. So right there, be careful with this, because if you just do the sign diagram, you might be tempted to say that that's a max or a min point. Hopefully you'd figure it out when you actually went back and plugged it in and got something undefined. But you could save yourself some work. Domain x cannot equal 0, all right? So I know that that's going to be an asymptote, a vertical asymptote. Okay, I'm going to make a note of that, vertical asymptote. Okay, so at this point, I can set up a sign diagram. And again, I'm going to do this both with the table and with the sign diagram. So if I set up the sign diagram, I have -1, 0, and 1. I already know that that's a vertical asymptote, so I'm going to label it again just to make sure I don't mess it up. And now we look at the signs of our first derivative. If I plug in -2,
It's gonna be negative, because it's not gonna be positive in the bottom.
okay, yeah, -2, it's -2 to the fourth, which is positive 16, so that's going to be positive on the top over a negative, so that's negative, which means my function is decreasing.
Are you plugging it in the derivative?
Yes, in the derivative. And I could plug it into this one, or I could plug it into this one, it's the same thing. So then I plug in, let's say, -1/2. -1/2 to the fourth is going to be a positive 1/16.
Yeah, so
-1 is negative.
negative over negative.
And a negative cubed is a negative, so that's going to give me a positive, negative over negative. So I'm increasing. Now, my original function was defined at -1, so I now know that this, I have a relative min, okay, is something at x equals -1. Alright, so might as well go ahead and do it now. If I plug in a -1 up into my original function,
You got
1 plus 1 over 1, 2 over 1 is 2. Okay, so my relative min value is 2 at x equals -1. So the min point, we could say, is -1, 2.
What, do you have a relative max?
Well, let's see, okay? I know I don't have one at the asymptote, right?
For sure.
So let's look at the other side of the asymptote. If I plug in a half into my first derivative, a half squared to the fourth is positive 1/16, but -1 is negative. And a positive, though,
It would remain positive. So
stays positive. So I have a negative over a positive, which is negative. This is why it's important to make sure I identify my asymptotes, because it sure looks like there's a max there if we were just looking at the sign diagram. Okay, a max at 0, but there's not. So now we plug in 2, positive 2 to the fourth minus 1 is positive, 2 cubed is positive, positive over positive is positive. So I'm increasing.
But at 0 there's a sharp change?
At 0, there's an asymptote, so it goes up to infinity, and then it comes down from positive infinity. It actually looks like this. Okay? So, this kind of got cut off a little bit. But yeah, and remember when we solved for 0, because it's squared, it would be a double root. And that's why you have it, rather than normal asymptotes, a lot of times asymptotes will go up to positive infinity, and then on the other side it jumps down to negative infinity and comes up again. Alright? Again, there you might be tempted to say it's a plateau point if you aren't paying attention to where your asymptotes are. Okay? In this case, because 0 is a double root of the bottom, it goes up to infinity and then comes straight back down to from positive infinity. Okay? So now we also know that there's a relative min at 1. If I plug in a positive 1 to my original function, I get 2 again. So I see here that the relative min is 2 at 1 and negative 1. Negative 1 and 1. So I have negative 1, 2 and the point 1, 2 as my 2 relative min points. My 2 relative extrema. Okay? Any questions about that? Alright, so real quickly, let me run through how to use this table again. If the table is helpful for you, go ahead and use it. It's kind of an alternative to doing the sign diagram. But notice the intervals here, basically the negative 1, the 0, and the 1 are what separate our intervals. Okay, so we'd have an interval from negative infinity up to negative 1. We'd have an interval from negative 1 to 0, an interval from 0 to 1, and an interval from 1 to positive infinity. Okay? We tested different values. We tested x equals negative 2, x equals a negative half. This is what we already did. We tested x equals a half and x equals 2. And when we did that, we got the derivative to be negative and then positive and then negative and positive. So that right there gave us our conclusion. We had a min here. We knew it was an asymptote. Okay. So that's a vertical asymptote. But then here we also had a min. And we would explain it's a relative min, it equals this, and so forth. Okay, we already have that written out. So it's just a different way of organizing your thoughts.
Is it an absolute min?
In this case, if we would have to pick some kind of an interval, but yes, in this case, for the whole function, 2 is the absolute min. You know, so for all the domain of the function, 2 is the absolute min because it increases on both sides of those.